Again, I want to apologize for missing last week. It was pretty unavoidable, but I feel pretty confident it won't happen again. So keep coming back here Mondays at 1 for these pre-lab lectures. And this week, like so many of the weeks from this point to the end of the term, these pre-lab lectures are going to become more and more critical because the labs are going to become more and more involved. They're going to be based on more and more new material. Today is probably the last time we'll see a lab where we don't have any math and we don't have any graphs. Today we're doing, or this week we're doing qualitative analysis, which I make akin to being detectives chemically. We are going to put on our detective caps and we are going to discover something in a sample. Now, I said that no graphs, and I said there's no math, but I also said that this is an important pre-lab lecture. So qualitative analysis, and some of you who have done 120 and already have done this kind of experiment, understand that while the actual protocol may be simple, if you don't understand absolutely what you're doing, the analysis is almost impossible. So today what I'm going to try to show you is how to interpret your qualitative analysis experiments that you're going to be doing this week so that you can be successful. So I think this is going to be an important pre-lab lecture. But before we begin, a couple of little housekeeping things. The first thing is it's that time of term again. It's time for me to be reviewed by all of the students. And so if you are hearing my voice, be it live or asynchronously, if you're watching this video, all of the people who are in Professor Tro's group who are taking the lab series will be asked to review this portion of the lab series. So even if I'm not your instructor of record, please go ahead and fill out that review that's been emailed to you. I want you to know that at no point will I know what any individual person said. It is completely anonymous. It will stay anonymous beyond this term. So just understand that this is your opportunity to give feedback into your own education. Is there something that I can do to improve? Is there something that you think should stay consistent with this lecture series? And this helps not only you and your future in the education within this university, within this institution, but then also it helps future students make sure that they're getting the best education possible by helping and tweak the instructors. You know, when I get those reviews, I look through them very seriously and make adjustments that are suggested. So please, if you can do that, it'll be really helpful. The second thing, of course, I'm just going to keep reminding everybody, I hope at this point everyone has their alum. If you don't, make sure that you're using spring break as your opportunity to get it and make sure that you have it, because April 12th, the week starting April 12th, we're going to have our at-home lab. It's going to be a crystallization lab. We're going to be recrystallizing alum, so you're going to need alum unless you're planning on making it at home by yourself, which is pretty complicated. So we learned that last term, remember? But you can just pick it up at the store. We're going to be focusing on crystallization. So make sure that you have that before that week of April 12th. If you delay and then you get to April 12th and I'm doing the pre-lab lecture and you're like, oh, alum, and you have to order it from Amazon and it's $6.89 plus free Prime shipping, but that's 2-day shipping if Amazon and the postal service is all working correctly, which is, you know, hit and miss these days. So that's at least 2 days into your week. So it's cutting into your 7 days to do that lab. So make sure that you have it before April 12th in hand and give yourself as much time to do that lab as possible. All right, let's get into qualitative analysis. And first, let's just define it. So qualitative analysis is the quality of something, not the quantity of something. So qualitative chemical analysis is a branch of chemistry that deals with the identification, simply determining what's there, of an element or a group of elements in a sample. The techniques can be very different in complexity, and it depends on the nature of the sample, depending on how many different elements or analytes are found in one sample. And more often than not, the world is a complex place. When we collect some lake water and we're looking for a toxin, it's not going to be pure water and just the toxin. There's going to be many other cations and anions and other species, bacteria and things present. And so as a result, often these analyses have to be systematic, and we have to make sure that we know and understand what we're seeing. Furthermore, I want to say that I think the overall takeaway of qualitative analysis is it is a way of examining a sample in which you, the viewer, the scientist, is the sensor. As soon as we begin to use electronic sensors, we tend to calibrate those things, and they very quickly become quantitative analysis. How bright the sample is coming into the sensor, we can associate maybe with concentration. We learned that last week with Beer's law, right? So we have, or maybe that was 2 weeks ago. Sorry, I'm catching up with the grading. But the point is that we took an analysis which is just saying the wavelength of absorbance. And as you're going to see in a minute, that's something that can exist in qualitative analysis. But as soon as we put it into this instrument with a digital sensor, we had new opportunities available in we could calibrate it, make a calibration curve, and then not just find out what is there, what wavelength that we're seeing being absorbed by this sample, but we can go one step further and say how much is there, which becomes quantitative analysis. So keep in mind that qualitative analysis happens mostly when the viewer is the sensor. And that sensor has to be calibrated. And that's what we're going to be looking at today, is the first part of our lab. And I'm going to leave the biggest part of our lab completely up to you to figure out. But the first part is going to deal with calibrating our sensor. But before we begin, almost every qualitative analysis lab that I've ever taught at any institution involves one of them, kind of a favorite qualitative analysis, which is flame tests. So we know that because of the quantum nature of individual atoms, they absorb and then emit very specific wavelengths of light. And so as a result, we can first calibrate and understand what colors different ions and different elements make a flame. Then we could take an unknown sample, observe what color it makes the flame, to deduce what element we think is present. So we can see that lithium, it makes a very specific red flame, while sodium plus makes a very yellow flame. Potassium plus makes a purple flame. So these are all alkali metals. Well, alkaline earth metals like calcium 2 plus, excuse my lack of superscripts, is about a reddish orange flame. Strontium 2 plus is more red than that, more red than orange. And then of course, barium 2 plus, that makes a kind of a greenish, almost an emerald flame. And then today, we're not going to be doing flame tests. Those don't show up very well in simulations, but we will be doing precipitations. We're going to see that lead makes a nice yellow precipitant in our simulation. And this is what it would look like if we were doing a face-to-face lab, what a yellow precipitate would look like. We've seen white precipitates already in this series, but this is what a yellow precipitate might look like. So that's giving us first an idea of one of the most common and really most fun aspects of qualitative analysis. But again, if we were to do this using the simulation, it would be pretty boring indeed. So we're going to focus mostly on precipitation reactions, which are a critical and very important idea in qualitative analysis because it tends to be pretty binary. You see a precipitate or you don't. And that's what we're looking for when we are the sensor, is as much of a binary choice. Did it dissolve? Didn't it dissolve? Did it make a precipitate? Didn't it? We don't want spectral results. So before we go on, I have to ask, and I'll wait for a response. Does anybody know what a group 1 cation is? I've asked a few students already, so if I've already asked you this, I'm not talking to you, but anyone I haven't asked this question to, we're talking about group 1 cations. Anyone know what that is?
It's just the metal in group
alkali
1,
metals.
right?
It's, tell me again, which metals?
Alkali metals.
Alkali.
Right, so thank you. So that was kind of the response that I was looking for, alkali metals. So maybe others of you thought a group 1, we think about our periodic table, it's separated into 18 groups if we don't consider the inner transition metals. And so group 1 would be the alkali earth metals. They form cations of 1+. Well, science is confusing sometimes. And just like the English language, if we say, I'm going to raise a barn today, I could say R-A-I-S-E, which would be to lift up a barn and make it. Or I could say R-A-Z-E, raise a barn today, which would mean to destroy it. Same sounding word, completely different meanings. Is anybody really trying to trick you? No, it's because the language, like science, is kind of always evolving with new definitions. And there actually is giant meetings of scientists who try to centralize and unify the language of science, but often things like this come through. So in qualitative analysis, we have a classification based on a series of precipitation reactions, and we group those cations into specific groups. So some of us might have noticed that we're using silver, mercury, and lead, none of which are alkali. They're not in the group 1 on the periodic table. They're not alkali metals. And so we can wonder, why are we calling them group 1? Well, this is how we're going to classify cations for qualitative analysis today. So if we take this group of cations, so there's a lot, including alkali metals. The first thing we can do if we have this mixture of ions, we can add HCl. And group 1 cations are defined as those that form a solid precipitate when mixed with HCl. And that is silver, mercury 1, and lead 2+. So those will form a solid when they mix with HCl. If we then take the remaining cations and we add hydrogen sulfide, then we are going to precipitate this collection of species, and we classify that as group 2. And we can see over here what's remaining in our solution. Then we can add ammonium sulfide, and we will precipitate out these species, which we classify as group 3. Finally, we can add ammonium carbonate, and we precipitate out these carbonates from these alkaline earth metals. And we say then group 5 is what's remaining, which ironically is what a lot of us were thinking were group 1 metals. So these exist, but they're classified in this precipitation, in this qualitative analysis, somewhat differently. So this week we're looking at group 1 cations, and that is this silver chloride, mercury chloride, and mercury 1 chloride, and lead 2 chloride. And so the question is then, if we add HCl, so if we started with this giant collective, and then we added HCl, all that we would be able to do is collect all 3 of these chlorides together. But the question is, what if we wanted to find out exactly what was there? Was it silver or lead or mercury? This wouldn't be enough. This is only enough to collect group 1 on its own. So today's experiment is saying, what if we have a collection of group 1 cations, that's silver, mercury 1, and lead 2, and we want to find out, is it silver, mercury, lead, or some combination thereof? Remember, often we're dealing with complex mixtures that involve more than one cation, and that will be the case this week. So we want to find a technique to individually and only determine whether silver exists, a technique to determine whether mercury 1 exists, and a technique to determine whether lead 2 exists. And then once we know those techniques work, then we'll be given a solution of an unknown collection of group 1 cations, and then we will apply it to determine what exactly is present in our species, or in our solution, excuse me. So
You're muted, Professor.
thanks. Sorry, I'm back. How long did you miss? Where did I stop? Been kicked out in the middle of a lecture.
Maybe like a minute.
A minute.
I would,
Last 30 seconds. I don't know how you guys
probably
know that. Probably on this slide. Okay.
um,
All right, we'll figure
I
it
would
out.
restart.
Let's see. Okay,
Like we had the little feature.
this one. Further back.
Yeah,
Here?
I would start from there.
Okay,
Yeah.
no problem, no problem. All right, so we just defined group 1 cations as this group within a series of precipitation reactions in which we can collect silver, mercury 1, and lead 2. Now the question is, if I start you all with a solution of the group 1 cations, can you find techniques to select and individually isolate each one of these chloride precipitates to determine what exists in our solution when I give you a solution of either one or multiple of these group 1 cations? Then once you have calibrated, you know what to look for, you've calibrated your sensor, again, we are the sensor, then you can look at an unknown solution and determine what's in there, like a true detective. Now, this is the key, and this is where I think we're going to find out this week for those that watched the pre-lab lecture and those that went for it, because this, you're only going to find in that background reading that I know some of us maybe skip through each week. This is the flow chart that's going to be really important for you to understand what each result means. If you try to simply write down the results of each of your reactions and you just say precipitate or not precipitate, you might be able to find your way to the correct solutions, but it's going to be a lot more complicated, like trying to see the trend on a graph by just looking at the data and not graphing it and seeing the line. So often just writing it down, what happens with students is they do the entire experiment perfectly. They get every result. And then you say, okay, what was in your solution? And they say, I have no idea. And the reason is because they haven't properly calibrated. They don't know what they're looking for. So what I'm going to do now is I'm going to walk you through those calibration steps, what you should expect to see. And I'm going to show you how those calibration steps flow through this chart. And then what you'll need to do then is take some unknown, create a protocol for you and your group, do a series of tests and properly identify what's there. So we'll keep this chart with us as we progress. Oh wait, before we progress, there's a few chemicals that we're going to be talking about today, which are particularly harmful. And so this is kind of a good and bad thing. It's good because we're able to explore some of these group 1 reactions with powerful chemicals that might not be able to be used in a Gen Chem lab. The other thing though is that we get to be a little bit complacent with some of these names, hey, 12 molar HCl, and we're not instilling the proper fear. And again, remember, the goal here is always to get into an organic chemistry lab or to go on and you do something with this education. And so we want to know that when we're seeing some of these chemicals, we're acting appropriately. So 12 molar HCl and 6 molar nitric acid are extremely caustic. They scare me. They cause serious tissue damage, specifically to your eyes if you're ever working with something like with this, or if anyone in the lab around you is working with chemicals like this. You really want to have goggles on, not because it's a rule, but because your safety is at stake. If you get it on your arms or your eyes especially, you want to rush to those eye wash stations. We've shown real pictures of what they look like before you enter any lab in any situation. You want to know where these safety locations are, how you get to the eye wash station, because remember, if you've got acid in your eyes, you're not seeing very clearly. The other thing that we're going to be working with today is 6 molar nitric acid and ammonia, which are dangerous to inhale as well. So we're dealing with chemicals that can be so strong, their fumes can be even fatal depending on if you pass out and where you fall near the chemicals, because they're heavier than air and can sink down. So if you get a big whiff of that, you start to feel dizzy, you want to get outside and get to fresh air as quickly as possible. One more thing is that we're dealing with silver, mercury, and lead, and all pose a toxic hazard to the environment. Mercury and lead, we know, would cause acute toxicity in humans. Silver is not as bad for humans, but it definitely has problems when it's uptake into the environment, and especially in the ocean systems. It can hurt creatures smaller, lower down on the food chain, which then has upward effects that a lot of us know of. So all 3 of these things we're not going to want to pour down the sink. You should always be aware of what chemicals you're dealing with, and just know that just because we're pouring it, we always have to pour our waste in the waste container in this experiment. But sometimes we know, hey, this is really just water. But today we really specifically will want to make sure we're putting our waste in the correct containers. When we get into the lab, when we get off to a job, when you're working in a lab, not all waste containers are created equal, unlike our lab simulation. And so you're going to want to make sure that you read the labels and put the waste in the correct container, because, and I'm not positive on this, but it's possible that some of these heavy metal wastes have to be disposed of differently. And certainly for chemicals, organics, and oxidizers, you know, those things definitely don't want to be mixed, because you can have inadvertent chemical reactions. And so specifically when we're dealing with toxic waste, in the back of your head, you should be thinking of disposal before the experiment begins. Okay, let's calibrate our sensors. So I'm going to keep this guide here, and we're going to walk ourselves down the branches of this tree. You still want to do this with your group. You want to be able to know in your head what you should expect to see, and whether at each one of these branches, which path you're taking, because with the unknowns, you don't know. For this test, we're going to know what we put in. So we expect to see and follow each branch appropriately. And this way, if we say we add hot water and we expect lead to dissolve, and it doesn't, we stop until we get the result we're looking for. Taylor, did you have a question?
Yeah, it was actually about the hot water. Would we have to like heat up water, or can we just, or do we just pour it what's in the
I'll
bottle?
show you in just a second. I'll show you in just a
Okay,
second. I'm gonna show
sorry,
you.
yeah.
Good. It's a good question though. And there, because yeah, the question is, what's the best way to add hot water? Should I heat up water and pour it into my solution, or do something different? So we're gonna see the best lab technique here. So we're gonna add a test tube. We're gonna just put our salt, our lead 2 nitrate in. So we're not gonna use a graduated cylinder this week. Does anybody have a guess why we don't need to use a graduated cylinder today?
Because it's qualitative, not quantitative.
Perfect. Yeah, because we're going to use an about amounts. And of course, you have to put an exact amount in the simulation. But if we were face to face, I would say, hey, let's use an about 5 mils, and maybe we would see what that looks like in a test tube, because we're looking for the presence of a precipitate, but we're not actually going to quantify how much precipitate we have. We're just looking for that binary yes or no. So you won't need to be using graduated cylinders, not because the simulation is getting lazy, but because this is qualitative analysis. So we'll add, of course, our 12 molar with care hydrochloric acid, about 2 mils. And as defined by group 1 cations, we'll see a white precipitate. So now we're going to pour off the liquid. So we might have some excess acid, and we're going to have our nitrate counter ions in solution. And so we're going to decant all of that liquid out, because we just care about the white precipitate. And so then, as Taylor asked, how are we going to add hot water? So we're going to do it by just adding regular room temperature DI water, 10 mils, and we should see that our precipitate persists. And then we will heat the water up. So we won't add hot water, we will add water, and then we will heat the solution. So we'll wait for 30 seconds. Here's my first pro tip. For this simulation, make sure you actually record how much time you wait, because once you get to the unknowns, it's either going to remain solid or dissolve. And if you weren't paying close attention while you calibrated your sensor, then you might say to yourself, did I leave it long enough? I don't know, let me put it back. But if you know after 30 seconds per se, I take it out and the precipitate has dissolved, well then next time when it's unknown, I'll wait 30 seconds and I'll take it out. And if I see a precipitate there, I will say I know confidently that there's probably not lead here. Of course, what I'm going to say today is the absence of something doesn't confirm it. So we need one more step. The other thing is that it's 100 degrees and we see it dissolve. But what happens when we take it out of the hot water bath? Not a trick question.
It cools down.
Yeah, it's going to cool down and the precipitate is going to come back. So you want to make sure, again, why you want to know exactly how long you've heated it up for, and then look immediately as you take it out, whether the precipitate is there or not. To have that additional confirmation, we're going to add potassium chromate, 1 molar, and we will see a yellow precipitate form. And again, you'll want to observe this for yourself. You can zoom in. take whatever observations and notes make sense to you, because once you're doing the unknown, you're going to want to make sure that you're aware what each step means. So that's going to confirm lead. So now we'll do the other branch. We'll do 2 at once for brevity. And so you're going to want to make sure you label, since we're going to now look for mercury and silver simultaneously. You want to label the containers. So here I just label it silver 1 and mercury 1. Of course, that's not exactly how the species exists, but subscripts and superscripts are not available for the label container. So you'll have to forgive me, but you can see it actually exists as mercury 2 plus. We call it, it's mercury 1. Each mercury has 1 plus charge associated to it. And we'll put our salts in, about 5 mils for each of them. And we will add our hydrochloric acid. Because they are group 1 cations, as we've defined today, we expect to see a white precipitate when we add 2 mils of each of hydrochloric acid to each. And that's what we observe. So now we want to do the same thing that we did before. We want to remove the liquid. We want to decant it off. So you'll push the decant button, and that will just pour off the liquid, and you will have your precipitate remain. The liquid will just go into the waste, and you'll discard those test tubes. And then, as we did before, we're going to add 10 mils of water to each. And now, if somebody can figure out how to put 2 test tubes into 1 hot water bath in this simulation, I'd be interested in finding out. But the way I see it, you can pretty much only put 1 thing in a hot water bath. Obviously, in face-to-face, that would not be the case. And we could put multiple things in a hot water bath without any penalty to our science. But for the simulation, I think we have to have dueling hot water baths. So your instructions say wait for 1 to 2 minutes. I would just emphasize that you wait longer than it took for the lead to dissolve, and to really record how long you waited, so that you can make sure that in the unknowns, you are doing the protocol the way that you calibrated your sensors, so that you're able to really be confident in your assessments after the fact. And so we take them immediately out, and we see that the precipitation persists. So it doesn't dissolve in any way. And so we then choose this branch of our tree. Once we add the hot water and we wait a minute or 2 and we still see the precipitate, we say that we either have silver or mercury. So now we're going to add ammonia. So before we do that, we're going to get rid of the hot water. So again, we're going to decant out the hot water and keep our precipitate, in which our silver chloride and our mercury 1 chloride are captured. We'll dispose of the waste, and we will put the containers in the sink. And now we'll add 6 molar ammonia. So I'm going to add it here on the lab bench. But if we were in face-to-face, where do you think I would add this 6 molar ammonia based on what I've already told you about safety?
Under the hood.
Yeah, we're probably going to go over to the fume hood where the 6 molar ammonia would be waiting, where the fume hoods are taking all those vapors and pulling them outside so that we're not hurting ourselves, and we would add it there. And so immediately we're going to add 6 molar to each. And so if we see a black precipitate such as this, we know that we have gone down this branch of the tree, and it confirms mercury 1. So we're going to have this complex, which is going to form either mercury, the black is just elemental mercury, and then the white precipitate at the bottom is this complex, this mercury ammonia chloride complex. If we see that the precipitate dissolves in the addition of ammonia, then we go down this branch of the tree, which indicates that we have added the ammonia and formed this silver chloride ammonia complex, which dissolves the silver chloride precipitate back into solution. Now, again, I've already said the absence of something does not confirm it in today's experiment. We could probably say, well, we think so, but let's think like real scientists. We want to have a binary test for each one of these elements that confirms them, doesn't say that something didn't happen, but says that something did. So our last step will be to add nitric acid, 6 molar, which is very caustic and needs to be done carefully. And that should reform the silver chloride precipitate, which is not soluble. And that would confirm the represence of this silver 1, or just, I'm sorry, the silver cation would be shown by the reformation of a white precipitate upon addition of nitric acid. So, okay, what's the whole point today? Well, first, I'm just going to keep highlighting, use this flow chart during your work today. I think not using this flow chart will make the experiment unnecessarily difficult. If we were doing this face-to-face, I would draw this flow chart on the whiteboard as you all worked to reference. So face-to-face or online, this kind of thing is really useful to not get lost in what does it all mean. I have a precipitate, it dissolved, it turned black, it turned yellow. What does it mean? This will help. This will help keep track of things. What I just showed you is simply the calibration steps. Everybody should do that so they know what they're looking for, but you're going to see in the post lab, that is a very small amount of what you need to turn in today. Here's where the real mystery begins. We're going to take two unknowns, and we are going to start by working as our group or working individually and make a plan. We want to make sure we know what we're doing so that we don't overthink something and fail to do the proper number of tests and possibly only confirm one element, one group 1 cation, one possibly 2 group or 3 group 1 cations exist. So make sure before you begin, you understand the process and your plan that you're about to do. Again, there is no procedural steps for this in the actual lab itself. It is asking you and expecting you to design your procedure ahead of time. So make sure that you've done the best test to check each one of these, the presence for each one of these cations in your sample. Don't forget, as I have said many times now, that they're often complex mixtures in qualitative analysis. You know, that means that there can be more than one thing, and we want that. We're trying to take these simulations, but we're taking this knowledge, we want to apply it to real life. We want to go get jobs. We want to become environmental scientists, nurses, doctors, engineers. We need to use this, and in real life, things don't really just occur a single element, a single ion in solution. They're complex mixtures, and today will be no different. And again, recording your observations carefully, especially during that calibration time when you are making the observations, because then once that goes away, once you're not putting lead in and you know what to expect, then you have to really rely on what you've already learned from those steps to know what you're looking at as precipitates form or don't form, dissolve, don't dissolve, turn yellow, black, and all of those things. So making those observations before you move on is going to be really helpful down the road. So as I was discussing before, here's what the post lab is going to be like. Question 1 and 2, that are the only 2 questions that involve what I have shown you today, that calibration. So a couple things just about those initial steps, but those aren't interesting. You put lead solution in, you know what to expect coming out. So that's not the point of today's lab. So starting in question 3 through 10, these all strictly address whether or not you're able to identify appropriately what are in these unknown solutions. You can see that there is a place to put written observations. So if you start making those observations right at the beginning, then once you hit the post lab, you're not having to go back and say, okay, wait, in that second test of the third thing, it's too confusing. So make your observations as you go, because that's going to be worth quite a few of your points this week. And then of course, you're going to have to identify what's in unknown 1. That gets you to question 5, question 6, 7, and 8 ask you what's in unknown 2. So your procedure must be robust. Otherwise, you're going to get to this point and say, well, I have no idea. And then whether, just in case you haven't really wrapped your head around the map of how to identify the cations in group 1, if you haven't really calibrated your sensor, this is when you're going to find out, because now you have a hypothetical situation. So you can think of it almost like a third unknown solution where you don't have to do the experiment, but you're going to be given the results, and you have to then take those results and figure out what was in solution. And that is about it. So the famous Sir Conan Arthur Doyle stole from Shakespeare, "Come, Watson, come, the game is afoot." You have any questions on this week's lab on qualitative analysis?
So you said that Well, we'll have to make a game plan to know. Would a possibility be with each unknown make 3? So you have to make 3 test tubes and like adding HCl, then adding the hot water, or do we need more than 3?
Yeah, no, I think that's, well, I can't see, there's only 3 cations, so I think 3 is a good number. And yeah, that's exactly the idea, is making sure. But then if you have sample 1, 2, and 3, you got to stay really, you have to know, okay, sample 1, I'm going to take, do certain tests. And then sample 2, I'm going to do different tests, and I don't mix those up. So however you approach it, you'd be surprised that if you don't write a few things down, you might be like, wait, what did we add to sample 2? Did we add ammonia yet? No, we didn't. And any one of those mix-ups is not going to yield what it should. No precipitate will form. And that might make you feel like something else is present that's not there. So just, I think that you're absolutely right. If your instinct is saying, hey, I'm going to separate this into 3 different runs of trials, all I'm saying is make sure that you're really clear with yourself, with your group, about what the plan is, label things, take notes so that you don't get mixed up halfway through. Good question. Other questions?
I have a question before we go.
Sure. Hey,
So
Manny.
for the at-home lab, it's just the alum, correct, that we have to get?
So far, to be honest, I haven't actually seen the protocol myself. That's one of my goals for this week, is to see that protocol myself. It's still being developed by other members of our team. But from what I understand, it's the only thing that we need. It's all I've been
Okay,
told.
at this moment. Okay, great, thank you.
And I trust that. So I'm not saying, I think we only need alum, but if anything else comes up, especially things like anything that needs mixing or measuring, all of those things, I will bring that information to you as soon as possible.
Okay, great, thank you.
Yeah, great question. Other questions?
Yeah, mine was on the analysis part, not really with this lab, but with the flame tests.
Yeah.
Does it matter what gas you use to make the flame?
Ah, that's a good question. So no, we use natural gas to make the flame, but I think what your question is, how do the colors of the flame impact the flame test? There's 2 things that we do there. So one, with a Bunsen burner, we have some control, and even in the simulation, we can adjust a little knob to change the heat of the flame. Remember, it's like a yellow and a blue and a purple flame on the simulation. Well, that's based on a real idea. We can control how much oxygen is mixed with the natural gas, and that determines how clean the burn is. And so we can take as much color out of the flame as possible. The other thing is that we can use actual optical filters to help take out. So there's a kind of glass called didinium glass, which if you hold up can take a lot of the yellow out that comes from the natural flame. And that can help you really isolate the color that's associated with the metal salt. So since I have you for a few more minutes and we brought this up, when have we seen this flame test in our lives? We've all seen it. When have we seen salts making colored flames, metal salts?
Fireworks.
Fireworks, exactly. So this has been known for thousands of years. We haven't known why, of course, for that long, but we have included metal salts into explosives, and we've seen colored explosions. And so we often observe this in fireworks. Exactly right. Great. Any other questions? It's going to be a fun week, but I really would take it seriously and take notes, because it's one of those things that can seem a little bit too easy until you're at the place where you're trying to answer the questions, and you can get yourself a little bit mixed around. So you take good notes, and I think you move right through this lab, and it's pretty fun. And it's something that's used in science today. So as a quick way of finding out what's present and what's not present in a solution. So if there's no other questions, I'll let you go so that you can all make it to lecture on time. Have a really great week in lab. Email me if there's any questions. Email your instructor of record if you have any questions, and enjoy your week.
Thank you.
Yep, you're welcome.